guys, and welcome to Learn Extra Live. Today in Physical Science for grade 12s, we are doing work, power, and energy, guys. I know that you guys love this part of physics, physics, right? Yeah, exactly. You guys love this part of it. So you guys need to join us on our Facebook page. That's facebook.com/Learn Extra, and our Twitter handle is @LearnExtra, guys. This is where you guys can ask as many questions as you can, Matrix. I know this section is demanding. I know that you guys have questions, so please jump onto the page. I'm going to be posting some awesome stuff on the page, so keep your eyes posted. Remember this link, guys. Remember it for the future, for now, for always. learnextra.co.za/live. Okay, do you remember that? Do you jot that down? I'll put it up on the page for you guys, because this is where you can get your notes, your schedules, your videos. This will take you directly to YouTube, guys. If you want to go into YouTube and check out our lessons, that is youtube.com/mindset learn. That's /mindset learn. You will see I've just opened it up here, guys. There's a list of videos of all our lessons. I mean, it's great, guys. If you guys need some revision, maybe tomorrow, or you've missed the show, or you have to miss a little bit because you have to cook or do something weird, then that's fine. You can just catch it on there, guys. Make sure that your full focus is here today. Thank you to Macmillan for sponsoring our lovely show. Over to you, Phil.
Thanks so much, Kat. Well, guys, as she said, some physics. Guys, get on the page, because we're going to be posting some links to some amazing animation, some interactive stuff that you guys can do. I'm going to be doing a few experiments here a little bit later after the first ad break. But before I do, I just want to introduce our topic today, and that is work, energy, and power. Now, last week, we took a look at how the work-energy theorem can explain how work is the transfer of energy, and that we can do a change of energy inside an object by applying a force over some sort of displacement. We're going to do a little bit of a revision, but not too much, guys. The show is online. You can go and download it. It's for free. It's all there with the notes. Okay, guys, you can see me again, but last week, you can go do a little bit of revising on your own. So as Kat says, get onto YouTube. Check out our shows. They are there. The pre-records are there. Okay, so now before I get too sidetracked and too excited about what is available online, we're going to start getting into what we're going to be doing in today's show. Okay, so here we go. All right, so now we're going to do a little bit of revision. So let's just grab our highlighters. And guys, please, the stuff is inside the notes, so I don't want you frantically writing down. But for those of you at home, we're just jotting down what's going on here. So it says to revise that work. Here we go. There's that word. I know you guys love work. As being the transfer of energy from one form to another. So the transfer of energy, and that is the definition, guys, of work. We're going to take a look at how I can transfer energy to and from objects. Now, last week, we stuck objects on flat positions, and we took a look at some angled forces, but we didn't actually take a look at planes, which were different angles. So that's what we're going to be doing today. And that's where our FET animation is going to come in. And guys, you know I love FET, and Kat keeps on posting up these links to FET. And I'm going to ask her to do exactly the same, because we're going to be playing around with a really fun animation. You can push things up and down hills. You can even flatten the guy. It's a huge amount of fun. A little bit sick, but
but fun.
But absolutely fun. Okay, what's physics if you can't destroy something? Okay, so now we've got to revise the idea that power. Now, guys, power is something that you last spoke about in grade 9. Okay, here we go. So power is the rate of transfer of energy. Here we go. So power, there we go. Power is that keyword, is the rate of transfer of energy. Now you might say, okay, well, transfer of energy, that sounds kind of familiar. Have I heard that recently? Absolutely, yes, I have. Because transfer of energy is work. Guys, please, your examiners are not out there to trick you, but sometimes they do phrase things in ways that I don't understand. There's so many times that matrics come out of their exams and they say, "Sir, I had no idea what they were asking. They use such complicated language." Okay, guys, here's one of the pieces of language which often confuses people. You've got to know your definitions, and that work is the transfer of energy. Now, when I define power as the rate of transfer of energy, wait a minute. Take a look at that. Transfer of energy, I know that. Transfer of energy is the work done on an object. Now, all that this introduces is the rate at which I do work. Now that's how you might remember power from grade 9. Okay, now here's something new. This is the interesting stuff. Now, I haven't seen it in too many of your past papers, but it looks like it's around about time for it to come back into your finals. So guys, you've got to be prepared for it. Power can be calculated in a different way. So there we go, power it is, and it can be calculated using the force applied to an object and the average velocity of that object. And it's quite important that you understand that that's a slightly different way of calculating power. In the past, I've just taken the work, divide by time, I get power measured in watts. But this time, I'm saying, okay, well, force multiplied by velocity in meters per second, and this is something quite weird, and this equals watts for some reason. Now, very, very confusing. We're going to take a look at it and how and when to use that formula. A lot of students say, yeah, well, here's my power equation. If I got force, I got velocity, I've got power. Guys, there are some limitations, so just hold your horses. Let's go through this slowly. And then as always, we're going to use work and energy principles to work through exam-style questions, okay? Now, they very often say, use work and energy principles to answer the following, because sometimes you can use equations of motion. Guys, if they say use the following energy principles, follow that. If you do it the other way, your examiners can give you 0, and that's not what you want. Okay? Not to make you scared, let's make sure that you guys are on board with this. Okay, so if you remember from last week that work is the transfer of energy, this is something very, very obvious. Okay, from last week, I know that my work there, W, what I'm going to be doing is I'm going to be highlighting it as I go through. So their work, which is W, and this is measured in joules, guys, because it's a transfer of energy. Now, a lot of you are saying, well, is it W or is it J? Now, let's just take a step back. When I've got an equation, I've got symbols. When I've got numbers, I apply a unit to identify what I've got. So if I see a J after a number, that means that I'm talking about energy or work. And W is a symbol for work. Now this is also coincidentally the reason that I don't like using W for weight, because W, for me, means work. All right, so let's move along in our equation. We talked about this equation at length last week, but let's just make sure that you're up to speed. Here's my applied force. Now remember that if you apply a force to an object, okay, and a force is measured in newtons, and we've got a displacement, okay? Now, something interesting from last week, we didn't have to have displacement in the same direction as our force anymore, because what I attached to the end of that is something quite cool. Because my delta x is my displacement, and that is measured in meters. There's something special right at the end here. Cos theta. Cos theta does something very cool for me. Cos theta makes sure that my force and my displacement are acting on exactly the same plane as each other. It works out the parallel component of the force. Let me just let that sink in for a second. Cos theta, if you remember from last week, works out the parallel component of the force. That means that now force and displacement can live happily inside the same equation, and we can get work which is measured in joules. So as long as I've got a force over some sort of distance, even if the angle is 0, you must show your examiners this. So I've got a couple of questions. Must I always use cos theta, even if cos theta is 0? And yes, guys, this is the equation. Now, you're not in grade 9 anymore. You can't use grade 9 equations because life is a little bit more complicated now, but not to fear. We've got an equation which always works every time with all forces, with all displacements, and that is the one. Guys, please don't be tempted to use F delta x. You've got to include the cos theta, even if theta is 0. Now, some people say, okay, well, what about cos 180? Cos 180 means that the force is in the other direction. Try it on your calculator. See what cos 180 does for you. Cos 180 makes this into negative work. Okay, now before we get too tied into negative and positive work, let's move on a little bit. I want to introduce the idea of power. So we're just planting the seeds. I'm going to show you what you should know and do know, but don't remember from grade 9. And then we're going to show you the really cool stuff. We are going to get into some of the experiments. We're going to talk about some of the simulations. And I'm going to tell Kat to post up the link. Have you got the link up to FET yet?
I'm going to put it up just now.
She's working hard on that. Okay, so the link up to FET, guys, will be on the page. And I want you to simulate those experiments with me. Please don't get too carried away. It's a lot of fun. And I actually want to show you what's going on when we do some of these things. Okay, so I just want to give you a little bit of a brief preview on what we're going to be doing a little bit later on. We've got this plank which seems to be resting on some books, and the cool thing about this is I can play around with a number of books. And the cool thing is it actually shows you the arrows with the forces of friction, the normal force, and the weight on the object. So guys, if you're having trouble remembering how to represent your forces from grade 11, very, very nice. As I start to change the incline, I can actually see the different sizes of forces. Okay, but now before we get too tied up with this, we can do some really awesome stuff with this. We can get our guy to push the object up the hill, or we can get him to push the object down the hill and maybe even get it to move down the hill. And we're going to be playing around with this and doing some work on this object. Eventually, we'll be able to calculate the power. If we manage to get a constant velocity, we're going to work with some apparatus. But before we get there, let's try and figure out what this power business is. Okay, so back into our lesson here. Right, power is the rate of work. That's how you remember from grade 9. Here we go. So the rate of work, or the rate of energy transfer. Those are just fancy ways of saying the work done on the object. So there we go. Once again, that power is defined as the rate of work or the rate of energy transfer. Well, there we go. There's our equation giving us power. Now, before I give you the unit of power or just remind you of the unit, it's going to be a bit confusing. So let's take a look at some of the other pieces. There's W for work. There's delta T, which shows me the time, and I've seen this before. This is my grade 9 equation to work out power. But P for power, and just remember it's capital P, small p means momentum. So capital P is power, which is measured in W. And you're saying, oh, Phil, why is there a W? There's two W's. Just remember that power is measured in watts. That's not the same as this W. This W is a unit over there, and this W over here is actually a symbol which represents the work done on an object. And remember, work is measured in joules. Guys, I want you to be clear on what you define as a unit and what you define as a symbol. It's quite complicated. There's just letters all over the place. But guys, P for power is measured in watts, W for work is measured in joules, and T obviously always measured in seconds. Okay, now I'm going to show you some really awesome stuff. I'm going to show you how we can combine all these old equations into some really cool new ones. Now, before you say, Phil, stop hurting my head with some maths, relax. You don't need to remember this. I just want to show you where your equations come from. Because a lot of you might say, okay, well, I've got this really cool equation. I can work out everything in the whole universe and I can get my Nobel Prize. And, well, that's no good if you don't know where the equation comes from. So for those of you that like asking why, and you follow your parents around and you're saying why all the time, I'm going to show you why we get this new equation, because it doesn't make a lot of sense on its own. So let's just point out some things which you guys already know or have learnt. Well, here we go. There's the first equation. This was a grade 9 equation which I learnt about work done on an object. I've told you that it's slightly outdated, that work, here we go, let's highlight it. So work is equal to force multiplied by displacement. All right, so well, that's kind of interesting. Now, this one requires force and displacement to be in the same direction. A bit of a pain. But now, is there something that we can do to combine these two? Absolutely, yes, there is. So, if you're paying close attention, I know that work is equal to F delta X. Let's see what happens when I put F delta X in place of work. I'm now doing simultaneous equations without numbers, and a lot of you are saying, oh, please, stop it. Okay, but it's not that complicated. Stay with me. Okay, now I don't want you to get too tied up in the maths, but here we go. So what I've done is I've said, okay, well, there's my work, and it's still over time, and that is still power. But there's something else which draws my attention, which makes a lot of sense to me. Delta X, change in X over change in time. I recognize that. I recognize that very well from grade 10. Change in displacement over change in time. Guys, that's velocity. So I've just pointed it out over here. So velocity is equal to a change in X over change in time. There it is in both of them. Okay, so what this does for me is this gives me a new equation describing power. Now, guys, before we get too excited about having a new equation to play around with, so this is like a kid with a new toy, I need to explain some of the bits and pieces that you need to be careful of. That power that I've just highlighted is still measured in watts. The force is still measured in newtons, and the velocity is still measured in meters per second. But here's a problem. Apart from the fact that I'm not writing very neatly, let's just correct that slightly. Okay? What I want you to remember is that there are limitations to this. The F and the V, first of all, those need to be in the same direction. And also, this V, because of the equation that I used, because it came from that one, I can only talk about average or constant velocity. So it's very, very important that I stress that this is used as an average or constant velocity. Now, there are exceptions to that, of course. I can use it in other places. So I can use it to find an average or constant power, especially when I'm doing a difficult job. This tells me how quickly I am doing a job. All right, now, what sort of jobs can we start to do with items like this? Okay, well, there's quite a lot that I can actually start to do with this. I can start to figure out how much energy do I need to put into a system every few minutes or every few seconds in order to get the job done. Now, power is quite a strange thing. A lot of people don't understand it particularly well. It's the rate at which I get something done. So if you're saying that I'm a very powerful mathematician, it means that I work through my work at a very high rate in a short amount of time. Okay, so guys, to let you recover some of your power, we're going to do a little bit of an ad break.
I think we should.
What about that? And then we're going to come back for some demonstrations.
Awesome. I can't wait for those. And I know that you guys can't wait for those. So make sure that you stay seated, guys. Don't move unless you need to do a bit of a stretch. But join us right after this. Welcome back, Mindsetters. If you have just joined us, which I hope that you haven't because we've covered such extraordinary work, we are doing work, power, and energy today, Matrix. And you guys aren't asking questions yet, but I know that you have those questions that are just niggling at the back of your mind. Please send them through to us, guys. Let's make sure that you understand this fully, like 100%. I want to make sure that all you guys have this section on lock because it's lots of marks and lots of really good marks that you really need to pass with that extra just to be above the rest as you mindsetters normally are. So please stay tuned and also concentrate, guys. It's really important that you guys are taking notes and you guys are taking regular breaks, which we do here. So you don't need to take a break right now because we've just come back from one, but make sure that you are fully aware of what you're doing just now. Over to you, Phil.
Thanks so much, Kat. Okay, well, guys, what I've got in front of you is a little simple piece of physics apparatus. This is called a dynamics trolley. Sometimes I see it inside some of your past papers. All that I've got here is a 0.5 kilogram weight, and with this, I'm going to apply a force to this object, and I'm going to get it moving. Now, remember what I said. To do work on an object like the dynamics trolley, I need to apply a force. Now, something like a weight is capable of applying a really nice force because it's got a steady gravitational force. That's called its weight. So now I've got this 0.5 kilogram force over here, and the 0.5 kilogram is going to be falling down with its weight, the gravitational force down to the earth. Now, in order to do this, what I've got to do is I've got to make use of a dynamics track like this and a very nice pulley system like the one over here. I just want you guys to come a little bit closer for a second and to check out what's going to be going on here. Okay, so now this string is nicely attached to my dynamics trolley on that side, but now it's run over a pulley. Now, I've seen this drawn in a lot of exams, and I hope you guys can see it very nicely, but the thing that I want you to really emphasize is that this is capable of changing the direction of a force and therefore of its movement. So this is my applied force in this case. It's going to apply its force through our string onto my dynamics trolley. So now, when I apply a force over a distance over here, so I start with my dynamics trolley, it's about to move, I've got stored energy inside my system, let's do some work on my dynamics trolley. Let's apply a force over a displacement and see what sort of energy comes out. So I've now got my displacement over here, and I've got my trolley. It's waiting to get its energy. It's waiting for the string to do work on it. The applied force is the one which gets the object moving in this case. Now you might ask, will it move all objects? And the answer is absolutely no. And I'm going to show you different things that we can do with this ramp in a moment to make sure that this doesn't actually move. Okay, so what happens is I've got my applied force. It acts over a certain distance. It's got an applied force of close to 5 newtons. It's just slightly less than that. I think it's 4.9 newtons. And then what happens is it's going to get this object to move over 0.5 meter. Now guys, you can figure out how much work that is quite easily. And we can even calculate how much power is exerted by the string. So how much power is being transferred to this trolley. Now let's actually let this go and let's see what sort of energy we get out. This one's probably the simplest of the experiments. Nice flat surface, and we just let it go. All of a sudden, we've got kinetic energy. Did you see that the trolley was moving? So let's just reverse that slightly. We had our force applied, and I think somebody was asking questions about that. The force applied was the thing which was doing work on the object. So my force was pulling in the direction of the string, and my displacement was in the same direction, and the time that it takes decides how powerful the other object is. Now, the only reason that I use this weight on this side, and I'm just going to bring this back into the frame, the only reason that I use this weight is because a weight pulls with a constant force. And that's quite important for another piece of work which we're going to do a little bit later. So now I've got this trolley and I've got this wonderful weight, and you've seen that this weight is heavy enough to pull this trolley forward. But is there any other way to get this to work where we can get these two objects stationary? Now somebody said, what is frictional force? I'm about to show you. Okay, so now the really wonderful thing about this piece of apparatus is that I can actually tilt it, and I'm going to ask you to watch what happens when we do tilt it. Something really odd has happened. I've still got the weight hanging over here, and I want you guys to watch closely. The weight is not being supported by anything. I've got my trolley over here. I got the slow creeping, but what we can actually do is we can get the system to move or not move, and this is really strange. Why is the trolley not moving? Guys, this is grade 11 revision. This trolley has to have a component of weight acting down the slope. Now you guys can calculate that. At the moment, the component of this trolley's weight, in other words, the gravitational force dragging it back down the slope, is equal to the tension inside here. So the applied force up is equal to the parallel component downwards. So what we can actually do is by changing the angle, we can get this to reverse rolls. And if I go far enough, eventually what's going to happen is our trolley is actually going to become the one which pulls back the weight. So we can go one way, or we can stop the whole system and we can go the other direction. Now guys, this is really good revision of our different components of weight. So over here, the components of weight is not large enough. As soon as I lift it back up, I want you guys to get really, really nice and close. Because of this angle over here, because of this angle, I've got components of weight which make this object slide down the slope. As soon as I increase the angle of the slope, that component becomes larger. Now, that's not the entire reason I've got this set up. This is a little bit of grade 11 revision of objects on slopes and components. Now, here's the really cool thing. What I can do is I can get this, and let's start this off at the bottom. I can have this pulling something up the slope, and if I get this just right, can you see that the object is slowly starting to creep? There we go. What do you notice about the velocity? The velocity is relatively constant. There's something really strange going on. Okay, well, I thought that if there's a resultant force, you're going to get acceleration. Newton 2 takes over and an object accelerates. So let me just do that again. It's a little bit tricky to get it exactly right, but once you do, something really cool happens, and there we go. We don't get that runaway acceleration anymore. We're getting relatively constant velocity. And I've done this a couple of times, and with this apparatus, I get around about 1 meter per second. Now, you guys can actually start calculating how much power is being transferred from my weight over here into this other object by the force of gravity. All you need is a force and a velocity. So you can figure out from 1 meter per second, 4.9 newtons downwards. Wait a minute, Phil. That's all I need to calculate power. And that's exactly what we're going to do when we go to our demonstrations. Kat, how's the page looking? And have you posted that wonderful link?
I've posted the link, and people are actually checking it out, Phil. They're loving it.
Okay, very nice. Well, what I'm going to do is I'm going to walk you guys with me to my board, and we're going to start playing around with that FET animation. Okay, so for those of you that are familiar with FET, right, something like this will not be unfamiliar. Right, we can see the animation pages over here. This is the page that I want you to be on. This is called the ramp. Now, the ramp is a way of simulating exactly what I've just done. You guys don't need a dynamics trolley. You don't need a pulley. You don't even need a weight. What you do get, however, is all sorts of really cool stuff that you can put on a ramp, lift it up and push it down, and you can start doing some of your own physics experiments. So there we go. We've got this object over here, and we can start to take a look at some of these forces. Now, it might be a little bit small on your screen, but what we can actually see is we've got this object sitting on a slope. And this is actually going to tie in very nicely with our exam question a little bit later on. What we can do is we can alter theta, which is the angle of the slope, and that's actually shown directly underneath the slope. Underneath the slope, and that's very, very nice. What that's doing, and you can see there's some books. So from a low angle of around about 4.9 up to a very high angle, eventually it gets to a stage where the gravitational component is larger than friction. So what happens is the object will accelerate down the slope. And I want you guys to play around with this. Please, forces explain everything inside mechanics. Please go back to your grade 11 books. Start talking to yourself about components of weight versus friction. So what I said to you was that I've got this weight, I've got this normal force, I've got frictional force on here. How do I start pushing this object up the hill? Well, if I start to apply a force in the direction of the motion, so here we go, we can actually start pushing. There we go. Here's our guy, he's pushing. At the moment, is he doing any work? Absolutely not, guys, because what's happening is he's not moving this cupboard. But the moment he starts to apply a force which is greater than a friction, what we start to find is that he can maybe push it. Oh, there we go. Let's push, push. Eventually, he can push it straight up the hill. And what we find is that my frictional force and my applied force are always going to be battling each other. What I'm finding is that this guy is doing work as he pushes the cabinet up the hill.
That guy's pretty strong, actually.
He is pretty strong. I saw him pushing pretty hard there. And we can actually follow how hard he was pushing on this graph over here. So it's pretty incredible. Guys, you can actually measure all the things inside here. And I want you to see the effect of the angle on the power of this guy. Now, you can follow the meters per second on the left-hand side, and you can find the force applied. So let's just do that again. Let's push our object back down the hill. It's much easier to push things down the hill than it is to push them up the hill. So he's pushing down. Can you see his velocity over there? So we've got a velocity there, like 1 meter per second or so, and it's going downwards. Now, what I want you to see is that I've got a graph underneath here. Guys, you can do your own power calculations. You can see how hard this guy was working just from his force and from his velocity. So let's just remind ourselves how we would do that. So here we go. What you would need is the exact force he was applying and the velocity at that time. Now, you can average it out. You can take several readings if you want. All you would need is his velocity. So let's just highlight the pieces which we can collect. So there we go, his velocity and his force. These are the two pieces of information that you can get directly out of the FET program. Now let's see how that changes because of an angle. So I'm going to start pushing up this hill, and we're going to start seeing his power. We're going to try to get him up to, and this is a great game, we're going to try to get him up to 1 meter per second. So this is going to require a good, strong push. And then what we can see is how much applied force there is. Okay, so we've got, all right, we've got an applied force, and we can see the applied force is very, very high. It's almost 500 newtons. This guy is really, really strong. So 600, there we go. We got to around about 600 newtons. I'm going to do this again. 600 newtons, 1 meter per second. Guys, this guy is incredibly strong. For short amounts of spaces, 1 meter per second times 600 newtons. Guys, that's 600 watts. 600 watts is a huge amount of power. Now, you can't do 600 watts for very long. Some gym machines tell you how much power you're giving out. Some pro athletes for long endurance races give out around about 200 or 300 watts. So this guy's really, really powerful. So let's do it again. Let's give out 600 watts over here. So he's got to work really, really hard. So watch that applied force over there. I've got a number down there, that orange number, which is climbing up. So it's going up, going up. As soon as I get up to enough, eventually, what starts to happen, there we go. Let's apply around about 600. All right, we're almost up there, and we got up to 1 meter per second again. So slightly less than 600 watts being applied to this box, and that's how much energy it takes to go up the hill. The question is, why do I have to do work to get things to go where I want them? Why do I have to do work to get the trolley to go to one end? Why do I have to do work to push something up the end? I know that I'm giving out a lot of power because I'm sweating by the time I get up to the top of the hill. Where does all that work go? Well, guys, the answer lies in this. I'm doing something for my trolley. I'm raising it to a higher level. So first of all, I am doing work against gravity. So I'm giving my object gravitational potential energy by raising it further off the ground. Now, something else which is quite important, and I want to bring this up, is the frictional force. The frictional force generates heat. When an object moves, it generates frictional heat. Guys, remember from last week that skater that was skating around in a skate park? The moment we introduced some friction, heat was generated inside the wheels. So the moment our very tired guy, you can see he's resting very nicely there. He's waiting to do some more work. There we go. He's pushing again. So he's got to overcome friction. But you can see that the applied force is much larger than the friction. So he's got to overcome some gravity as well. So this guy is doing work against friction. He's doing work against the gravitational force, and I'm trying to keep this a nice steady velocity, and you guys can play around with this all you like, because you guys can play around with some keys on there as well. You can drag it with your mouse if you really want to get some fine control. Really, really awesome to do this on the touchscreen, so I'm glad that they let me play around with this machine. All right, and then start to take a look at the work which he has to do when he goes down. Why does he need to do less work, less power, when he's going down the bottom? And we can see that the cupboard actually eventually rode over him. This poor guy. Okay, he did all that hard work and the cupboard rode over him. Okay, so this poor guy, let's get him back on his feet, and we start pushing up. So a large amount, and you can actually see the arrow over there, huge amounts of applied force. And we're only getting up to just over 1 meter per second. You can actually see the power from there. Okay, so guys, I want you to play around with this. Something else which I want you to play around with is the effect of that angle. Well, you might say, okay, well, is it easier to do it at 14.2, or let's take it down to around about half, so 17.1, I think I had it over there. Let's try and get this accurate, so there we go. Oh, almost. Okay, but we've got to roughly half the angle. Will it affect the amount of work which he has to do? So let's push our cupboard back down to the bottom, right, and then eventually we're going to push it back up the hill. So there we go. He starts pushing. I want to get up to 1 meter per second. Let's watch it very carefully. 1 meter per second. It's almost there. There we go. All right, we're up to 1 meter per second, but we needed to apply much, much less force. All of a sudden now we only need to apply about 300 or 400 newtons. You can see that the power that's needed to climb a shallower hill is much, much less. Now I want you to think about this. When you're driving in a car and you're driving up a very steep hill, I want you to watch the relative speed of all the cars. So the less powerful cars with smaller engines or heavier masses very often will struggle to go up that hill at the same velocity as any of the others. The lighter ones, or the ones with stronger engines, are able to climb the hill. This is because of their engines. Their engines are more powerful. That means that they can do the same amount of work, in other words, climb the same hill, but they can do it in a much shorter space of time. Guys, while I let you play around with this, and we're going to come back to our exam question after this, I think it's time for a break, eh?
Thank you, Phil. I think it is time for a break. Guys, this FET website is absolutely fantastic. I hope that you guys have jotted it down. They are on the page. I hope you write it down, take it to school tomorrow, try it at school, give it to your teachers. It makes learning really easy and really fun. So play with that during the break, and we'll see you right after. Welcome back, Mindsetters. I see the page looks absolutely fantastic. You guys have really come out in your numbers today, which is great to see. It just means that more of you are getting such fantastic knowledge. Without further ado, I'm going to hand over to Phil because I know that there's a lot to go through. And I hope that you guys have downloaded those notes, guys. They are really important. And it makes learning so much easier when you're following along with what you have. Download them on your phones, on your computers, anywhere you can. And even print them if you want to. Over to you, Phil.
Thanks so much, Kat. Okay, well, what I've got here is an exam question, and this is from the November 2009. This is question 5. Okay, so let me actually write that down for anyone that's on the page. And guys, if you follow in my notes, there's a link up to the Department of Education past papers. So 2009. Okay, just be careful. There are 2009 papers available on the website. This is one which was actually used. So this is November 2009, paper 1, guys. Paper 1 is the physics. Okay, so paper 1, right, here we go. So we've got John applying a force F to help his friend in a wheelchair to move up a ramp of length 10 meters. So here we go. They've got a very nice drawing there for us and a vertical height of 1.5 meters. Okay, so quite important that they've told me the vertical height there, as shown in the diagram below. The combined mass of his friend and the wheelchair is 120 kilograms, because mass very often is useful for calculating my kinetic and my potential energy. Now it says the frictional force between the wheels of the wheelchair and the surface of the ramp is 50 newtons. Now guys, just remember that friction always acts, and in most cases here, if I've got an applied force and there is friction, friction is usually acting in the opposite direction to the motion. It's stopping the wheelchair from going up the hill. Now it says the rotational effects of the wheels of the wheelchair may be ignored. So we're talking about any rotational energy and stuff like that. Guys, don't get too tied up in that. Don't worry about the rotational effects. Okay, so a little bit of fancy terminology, but don't worry about it. Now it tells me that the wheelchair moves up the ramp at a constant velocity. Guys, this is quite useful. Okay. I'm going to elaborate a little bit later on if we've got a little bit of time. I'm actually going to give you a velocity, and then I'm going to do P is equal to F times V. Because we've got a constant velocity, this is ideal. But the problem is there's usually a couple of steps before that that involve the work and energy theorem. Okay, so they've asked us to do something very, very clever. They've said, what is the magnitude of the net force acting on the wheelchair as it moves up the ramp, and give a reason for your answer. Okay, so now let's just take a look and let's see what we've got and pay attention to the mark allocation, guys. It's only for 2 marks. One of them will be for your answer, one of them will be for your reason. For 2 marks, it's very seldom expected that you do any sort of calculation or massive free body diagram. We can do one if you really want, but guys, it's not necessary for 2 marks. So let's spend our time on the things which do get us the marks. So here we go. We've got the magnitude of the net force acting. Oh, wait a minute. I know for this guy moving up this hill, I know that he's moving at a constant velocity. They've actually given me a very big hint. That constant velocity means that there is no acceleration. If there's no acceleration, there's no net force. Okay, guys, here we go. So there's your explanation and there's your answer. So we can say, if you want to explain it in terms of Newton 2, you can do this as well. You can say that F net is equal to the mass of the guy times by his acceleration. Well, we know that his mass with the wheelchair is 120 times by an acceleration of 0, because there's constant velocity. That's still equal to 0 newtons. So all the forces added up on this guy add up to 0 newtons. Now, guys, that is equilibrium. Now you might say, Phil, how is it possible that this guy is in equilibrium but he's still moving? Please, please, please don't make this error. Equilibrium just means that I maintain my current state of motion. That means that I stay stationary, I stay where I am, or I stay moving in the way that I was. Newton 1 is applying here. All the forces are balanced on our guy inside the wheelchair. So Paul is doing a good job keeping the constant velocity headed up the hill against friction and against the weight, but he's not adding to this object's kinetic energy. Now you might say, Phil,
when did they actually manage to talk to you about kinetic energy? Well, if I read a little bit further, let's take a look at our question, and it says, what is the magnitude of the net work? Okay, wait a minute, this is something new. The net work done on the wheelchair on reaching the top of the ramp. Okay, so this is net work. All right, well, let's just write it down and let's see if we can get some ideas. So the net work. Okay, well, wait a minute. I know a formula for the net work. And if you were watching closely last week, the net work on an object is equal to the change in an object's kinetic energy. So EK, or guys, you'll see it on your formula sheet. Sometimes it says delta K. They don't mind which one you use because both are on your formula sheets. Okay, so let's work with this. The work done by the net force is equal to the change in EK. Here's the really magic part. Well, there was no change in the EK. So that is equal to 0. How do I know that there's no change in kinetic energy? Well, guys, let's pay attention. There it is. Once again, they're trying to plant the idea of a constant velocity. A constant velocity means no change in velocity. So no change in kinetic energy. Remember that kinetic energy is the energy of motion. If there is no change in motion, there's no change in the kinetic energy of this object. Now we're going to get into the interesting part of this question. So it says, what is the magnitude of the net work done on the wheelchair reaching the top of the ramp? And eventually we're going to get to the power of Paul if we get some time. Okay, so here we go. So we've got this wheelchair moving up the ramp at constant velocity. Here we go. Right, and then eventually I'm going to include something of my own. It says, calculate the following. First of all, the work done on the wheelchair by the force F. Now 5 marks. 5 marks tells me that there must be some sort of calculation going on. So work done on the wheelchair by force F. Well, let's look at our diagram, guys. Let's see what force F has actually got to do. Well, there's a few ways of thinking about this. Okay, so force F acts up the hill. Now, I find this diagram to be slightly confusing, and I prefer free body diagrams. The reason that I prefer free body diagrams is I can put these arrows wherever I want. So let's do exactly that. Let's just draw in another hill quickly. So let's have a green hill. So the wheelchair is going up a green hill in this case, and we know that this hill is 10 meters long. So what are the forces which are acting in the same direction as the motion of this object? Well, force F, we know, is acting parallel to the hill and up the hill. So let's just label it F as it goes. Now, there's a whole bunch of other forces, but what I'm going to do is I'm going to concentrate on the ones which are working against F. Here's the reason. I know that all the forces acting on this object, parallel and perpendicular, add up to 0. How do I know this? Well, they told me that the system is in equilibrium. The way that they told me this was that there is no net force. So let's take a look at my diagram and let's figure out what the other forces are. So what is force F actually trying to do? Well, let's see. So it says the work done on the wheelchair by this force F. Well, we know that we've got a distance of 10 meters. We know that force F is working against other forces to move it all the way up the hill. We know that all the work added up adds up to 0. So now it says the work done on the wheelchair by force F. Well, how do I do this with the information which I'm given? Well, before I start deconstructing all of this, I need to approach my work energy theorem, and let's do this with a little bit of caution. Okay, so already we established that W net is equal to the change in kinetic energy. Well, there's several types of work which is being invested into this object. There's work done by the applied force. So let's actually call that work F. Because it's force F, let's use work done by F plus. Now there's other types of work, remember. There's work which is done by gravity on the object. There is work which is being done by friction on this object. Now I've got to be very, very careful, but I do know that my kinetic energy change is 0. Okay, so very, very cool now. Now we are looking for this term. The work done by gravity. Now this one is quite a difficult one in the way that you do it. Okay, now I've got to realize that the work done on gravity is going to be negative work. Now I haven't talked to you in much detail about this, but work which decreases the energy of my object is called negative work. And the way that I find negative work is by investigating the angles correctly. So let's do work on gravity separately. Let's actually just make a little subtitle to work out my work done by gravity. So work done by gravity is equal to the force of gravity, and we know how to calculate that, times the displacement that was moved by the object and cos of the angle between. Now this is where it's about to get a little bit complicated. Between the actual displacement and the force of gravity. Now you might say, but we've been given an angle. Right? We can actually calculate this. We can play around with it. We've been told that the slope is 10 meters long. And we know that it's a certain height. Let's just check our information again. I think, there we go, it's 1.5 meters high. So it's 1.5 meters high. So we've got two displacements. Which one should I use? Well, when I'm using this formula, I have to use the displacement of actual movement. And herein lies the problem. Let's draw in my force. So there's my force. Where is my displacement? Well, let's draw in my displacement. Let's just make sure that everyone understands where my displacement is. So my displacement is 10 meters up the hill. What is the angle between them? Now, guys, this is going to require a little bit of calculation. So I'm actually looking at that angle. And this is a little bit of a pain. I'm going to have to do many, many different steps. There is an easier way. Now, my work done by gravitational force, and this is a little bit of a trick, and it is allowed to be used, is that work done by gravity is equal to the negative change in potential energy. Now, where did I get that from? Well, guys, this already introduces the negative part of this, the force gravity, and the delta x with the cos included. So what this does is this already calculates for us the work done by gravity on my object. Now, it should be a negative number. It's got to be a negative number. And the reason it's a negative number is because gravity is stealing energy from the wheelchair. Okay? So let's actually go for this. So I've got negative. Now, what was the mass of our wheelchair? 120 multiplied by 9,8 multiplied by the change in height, which is 1,5. So I've got negative 1764. So let's just make sure that we've got our substitution because you guys are making notes. So I've got 120, 9,8 over there. My change in height, which is 1,5. And let's just remind ourselves of that number. So 1764. So there we go. 1764 joules of energy is taken away by going up this hill. So there's two approaches to finding work done by gravity. This is by far the simplest one. If you'd like to, you can go and calculate that angle over there by using 10 as my hypotenuse, 1.5 as my opposite. Use sine and you can find out that angle and add 90 to it. But guys, unless your trigger is very good, I would suggest that work on gravity is negative change in potential energy. Okay. So now we've got my work done by gravity. So that's really good. There we go. We've got work done by gravity. What about work done by friction? So somebody said, what is the frictional force? How do I calculate it? Where does it come from? How does it act? Now, let's draw another little diagram. I'm big on diagrams. I'm sure you notice. I'm not the best artist in the world, but I love my diagrams. Friction acts against the wheelchair, pulls it back down the hill. So here's my frictional force. So my frictional force is acting backwards. Now guys, the displacement is up the hill. So there is my displacement. What is the angle between those guys? Well, this one's really easy. No big trig involved. Work done by friction is equal to, well, it's my frictional force multiplied by my displacement multiplied by cos of, guys, for a straight line, my angle is 180. This is a negative form of work, and I'm going to show you why. So let's just remind ourselves what the frictional force was. The frictional force over here is 50 newtons. It's inside my information. So let's use my 50 newtons. Let's use the displacement of 10. So there we go. We've got 50 multiplied by a displacement of 10 multiplied by, and cos 180 is negative 1. So what we've got here is negative 500 joules. Okay. So I know that friction is taking away a further 500 joules. Let's put it all together. 1764 and 500 both together. Let's put it back into my work energy theorem. So work done by F plus work done by gravity plus work done by my frictional force is equal to 0. Now, work done by F is what we want. Work done by gravity is negative 1764. Work done by friction is negative 500. And that all adds up to 0 because the object is not gaining any speed. So this is actually really easy to do. So what I'm going to do is I'm going to subtract a further 500, take it across to the other side, and what that would do is multiply it by negative 1, so 2264 is my answer there. So I've got my work done by my frictional force. 2264 joules of energy has been invested by Paul going up the hill. Now, what I'm going to do is I'm going to give a little bit of a challenge. We're running a little bit short on time, but I want to push you in the right direction. So what I'm going to tell you is that this wheelchair is capable of going up this hill at 0.5 meter per second. All right. So what I'm finding is that this wheelchair is going up there at a constant velocity of 0.5 meter per second. Guys, I want you to calculate the power. And to do that, I'm going to need to solve this next piece. And lucky for us, this one's really, really short. It says the magnitude of force F exerted on the wheelchair by John. Now, guys, this is probably the simplest of the calculations that we've bumped into this evening, because part 2 allows us to use our magic equation. So there we go. So work done by F is equal to F multiplied by my delta X and cos of the angle between them. But lucky for us, I'm looking for F. My displacement is 10. Cos theta is cos of 0 degrees. And my work is 2264. And what that allows us to do is divide through by 10. And my friction is equal to 226.4 newtons up the hill. Now, guys, that's what you need to calculate the power. Guys, go for it. I want you to try and use the applied force. Remember the applied force pushing the wheelchair up the hill. You can work out, using the velocity, you can work out the power of Paul. Now, if you download those notes on the website, I've actually given you a really nice challenge on cyclists. Cyclists can maintain a really nice steady velocity. I've actually asked you to work out the frictional force of a cyclist, which can give out 300 watts and is able to maintain a certain speed on there. And you can actually calculate how much friction they're working against. You'd be surprised at how little it actually is. Kat?
Thank you, Phil. What an awesome lesson it was, hey?
I enjoyed it.
Thank you. And I know you mindsetters really did enjoy it. I want to urge you guys to really, really take up this challenge, guys. I know how you guys love challenge questions, so do it. And maybe send us your answers on the page, and we'll be more than welcome to look at them, guys. So now, what I need you guys to do is have a great evening. Thank you for joining us today. It's been fantastic. And thank you to Macmillan for proudly sponsoring our show. We really appreciate it. Guys, do more learning. Do more anything that you need to do, guys. We'll see you next time. Bye.